So welcome to this Geographic Information Systems and Water Resources offered through the CUAHSI Virtual University. I'm showing here the Canvas web that it will be used for the class, and all of the material that's is made available to you will be linked here. So probably a good place to start, at least for today's lecture, is this announcement that I posted this morning that has the slides that I'll be showing. It has the course outline and schedule that I'll be going through. And it has what I'm calling Exercise 0, which is an ungraded exercise. That's the pre-course self-assessment. So let me open the outline document. That's a PDF document. And in that, I've just given some of my contact information. There's a phone number, that's my office phone, and probably best to contact me by email if you need to discuss anything with me. And that email is, you can also contact me through Canvas, which also effectively email. There's a description there which talks about the content of the course, and that's the same as what was advertised in the CUAHSI Virtual University syllabus. And there's a statement about the prerequisites. We're using ArcGIS Pro from ESRI, and because this course has to be condensed into 8 classes, 4 weeks, I'm hoping that, well, I'm going to pretty much jump right in with the hydrology and water resources content and expect you to learn the basics of ArcGIS by following this module. And I worked through that a few days ago, and it's not too hard. And we'll also talk a little bit about it. The course objectives are given here, and I've also got a slide about those, so I'll maybe go into those. This is the link to the Canvas website for the course. This talks a little bit about the accounts that you need to be able to use ArcGIS Pro, but the bottom line really is that if you're having any trouble, please get a hold of me. Each of the participating universities has a site license, so we do have permission to use. You should all have permission to use this, but sometimes it takes a little bit of working to get the kinks sorted out at the beginning. And I've worked through it enough times that I usually know what are the right questions to ask in terms of helping people get going with this. There's no specific textbook, but I'll be putting readings and handouts in Canvas. For the grade, there'll be 4 exercises, and I will just take an average of that and assign the grade. And then the schedule is we meet on these 8 occasions. It'll be basically a lecture interleaved with exercise, and then you'll have to hand in the exercise about a week after they're assigned. So that's going to be a sort of very compressed run through basic assembly of a watershed base map, spatial analysis and hydrology, where we'll look at how to interpolate rainfall over a watershed and then compare that to stream flow and a bit of a water balance. Then digital elevation model, watershed delineation, and then a bit of programming, which will also get into height above the nearest drainage. So I've got some PowerPoint slides that I'll go through, but let me pause just a minute and see if there are any questions from any of you. And was anybody from CUAHSI actually able to join yet?
Hi, Dave. It's Emily. I'm here.
Okay, you're good. All right. Seems like we're all going and the recording is going.
Yes, you sound pretty good, so I'm here if you need me.
Okay. Any questions from anybody else? Okay, let me switch back into my slides. And I've somehow got to get this GoToMeeting thing out of the way. So I'm at Utah State University. I've been a professor there for 29 years, and I direct the Utah Water Research Laboratory. A lot of the material that we're covering was given in an online course with between University of Texas and Utah State University over the last 20 years with David Maidment. He has retired from teaching, so I decided to offer a subset of that content available through CUAHSI Virtual University, and I'm excited to be able to share this with you. So the learning objectives: by the end of the class, you should be able to prepare a base map of a hydrologic region, including watershed, streams, topography, land use, measurement sites, and data measured at those locations. And the first exercise will focus on that. You should be able to interpolate measured data at points to form raster surfaces over a region, and spatially average those surfaces over polygons of interest. And that'll be done in the context of rainfall, and that'll be the second exercise. Do hydrologic calculations using map algebra on raster grids. So that'll also be part of the second exercise, and you'll learn how to manipulate and work with geographic data in ArcGIS. Analyze digital elevation model of the land surface to derive watersheds and stream networks. That's been a lot of my research over the years, and that'll be the third exercise. Calculate hydraulic properties of stream channels from a digital elevation model using the height above nearest drainage approach. This is a relatively new approach that we have developed, and the papers on that are just coming out. And that also will get us into programming, because that is part of what we use programming for. Programming for is to automate and extend GIS work. So there's the schedule, which I went through when I was showing you the outline PDF document. So we're going to be working with ArcGIS software. So ArcGIS is really the leading commercial software that's available for work with geographic information systems. Sometimes people say, why don't we use free software like QGIS, for example? The fact of the matter is that with a big company behind it, ArcGIS is incredibly powerful, and often using professional tools is what you need to do to get the job done. And we're fortunate that in a lot of our universities there are site licenses, so we get to use it at no additional cost to us. But it is relatively expensive, but you get what you pay for, really, and it really enables the analysis of geospatial data in a really effective way. I've got here some pictures of Jack Dangermont, who's the president of ESRI, the company behind ArcGIS. And I would encourage you to go and look at this New York Times article about him, because it sort of puts him in a personal light and lets you see the sort of care that somebody at the top of a multi-billion-dollar company puts into everything he does in life and his work. And I've seen him speak when I was at an ESRI users conference. I haven't been to very many of them. David Maidment has, I think, been to all of them, and he brought this article to my attention. This is a screenshot from his presentation at the ESRI users conference in 2018. And you can follow that link to watch it on YouTube. And I would encourage, again, to get a sense of some of the sort of vision that ESRI is bringing to what they're calling the science of where, which is what geographic information analysis is all about. And this is one of the slides that he uses in that, pointing out that geospatial systems are helping us understand. So one starts from data, integrates data together into information, then it becomes knowledge when you can combine different layers of information together. And really, when people start working with information and knowledge, that's how understanding is generated decisions are made, and the world is made to be a better place, hopefully. So helping us make better decisions by integrating a lot of information. And geographic information systems are really good at integrating information from multiple sources. And we'll be thinking about the structure of how that comes about. So I want this course not only to be about how to do things with GIS, but also think of the place of the doing that in the context of solving problems, making better decisions by combining information. And if you think of it from that more abstract perspective, I think you can perceive it as a science rather than just a set of tools. So I wanted to start off with just a little bit of philosophy, which I went over there. But I realized that many of you will be somewhat new to GIS. Some of you will have learned in earlier versions of the software. I know a lot of schools are still teaching with ArcMap, the earlier versions of ArcGIS. So to get us all on the same page, I put this link, and this was also what I put as the prerequisite for anybody who didn't have any GIS experience to get up to speed. So this is a learning module that's prepared by ESRI, going through the basics of using ArcGIS Pro. At the end of it, you end up with this map of deforestation in the Amazon, which is actually kind of apropos these days with the fires that we've had there recently. And here it may be too hard to read on the screen, but this is also in the self-assessment exercise I've set. These are the skills that I identified when I went through this exercise. So these are the sort of things I expect you to be able to do. Create an ArcGIS Pro project, open and close it, import data from existing map project. And what I'm asking you to do is actually just read that, and you're not going to be, this is effectively for you to honestly work out for yourselves how much you know about the subject to sort of get yourself prepared. So assess whether this is an item you don't know, and if that's, put a 0. If you maybe know it, put a 1. If you're confident that you can do it, put a 2, and then sort of add them up. And I'm saying, well, if you get 40 or above, then you're a pro. If you're somewhere less, it's a little bit less. So let me get out of the presentation. I think that what I've made available on the Canvas site, if you look at the assignments, the very first assignment, which I'm calling exercise 0, you guys don't see the this one yet, because that's my work and getting ready for the rest of the class. The pre-course self-assessment of GIS knowledge. Basically, I'm asking you to download this document and fill these out. And I said if your score is 40 to 60, you're a pro. 20 to 39, some review and practice is needed. 0 to 19, take the time to do the getting started with ArcGIS Pro lesson. But then as I've reflected on it, I've thought that I'll actually make just going through that lesson the first part of the exercise 1 anyway, because it's really useful to get everybody on the same page. I've also put another set of questions in this pre-course self-assessment, basically created a space for you to tell me what you know about GIS, what you'd like to learn from this module, and a bit about your background, what university and department you're in, the degree you're working on, and why you're taking it. So I'll read these mostly just to get to know you and get a sense of some of the things you're interested in, and then to the degree that I can and the time available would sort of adjust the delivery to match your needs. And then the sort of yes or no questions. Have you been able to open ArcGIS Pro? And did you do the module? And if not, well, maybe you already know ArcGIS or some other reason. So fill that in, and I think I put a deadline on that by Thursday so that I can start reading them over the weekend and get a sense of who you all are in this class. So let me get back into the slides. So now I'm going to just overview some of the exercises that we'll be doing. The first exercise is building a base map. And the goal of that is really to create a database for a particular watershed that has a collection of thematic layers. This is the base map for the San Marcos Basin, and I'll be in the exercise writing detailed step-by-step instructions for you to do that for the Little Bear Logan River Basin, which is one of the watersheds near Logan, Utah, which is where Utah State University is located. If you're ambitious, you're welcome to do this for your home watershed as well, although it might be slightly easier to do it for the watershed where I've provided an exact example. And that will provide experience working with GIS data sources for hydrology and water resources, map projections and coordinate systems, querying and selecting and analysis of data. There's a typo there that I'll have to correct. And then geodatabases, feature datasets, and feature classes. The second exercise will be looking at rainfall data over a watershed from point rain gauges, and then looking at different ways to interpolate and estimate watershed average rainfall. And that also gets us into the capabilities of using the model builder components within ArcGIS to automate some of that. It's really a visual type of programming. Then we'll get into watershed and stream network delineation, creating a detailed set of watershed and stream network features from a raster terrain model. We'll talk a bit about what a raster terrain model is, but it's basically a representation of the topography. And we'll be able to do that with online data services, as well as with the hydrology toolset that's built into ArcGIS, as well as with the Towdem software, which is software that I've developed over the years that has some specialized functionality for watershed delineation that I'll briefly introduce to you. Then the last exercise will get us into flood inundation analysis, where the idea is if you've got a reach of stream, you can calculate the height from every point on that watershed down to the stream, going down sort of downhill following flow directions or looking in the straight direction. That's referred to as the height above drainage, or height above the nearest drainage, or hand. When you take that combined with you've got the height above drainage shown there. You can look at the streams as well as the catchments. And then if you've got a model that's providing the depth of flow in each of those streams, you can then map the grid cells that are less than that depth of flow. You can identify what houses may be in that area that's inundated and how deep the water is. That's something that's pretty important for flood mapping, real-time flood forecasting, as well as planning to make sure that we zone things properly and don't allow construction of at least critical infrastructure in houses where people are going to be living in areas that are going to get flooded frequently. So that's an overview. What I'm going to do for the balance of the lecture is talk about some of the core GIS concepts that we rely on every day, but it's maybe worth pausing and just seeing if there's any questions at this point before I go into that. No questions. Okay. So geographic information system is a system designed to capture, store, manipulate, analyze, and manage lots of types of geographic data. It's maps, data, tools, working on computers. Really, geography is visualized in maps. And here we have a map of Austin with UT Austin highlighted there. And you can zoom in and identify a specific address. These maps in GIS are built from data such as where the building polygons are as shapes, where they're located in the earth, as well as attributes such as the name, the type of road, perhaps other attributes like the speed limit, and things like that. We use what's called vector data to represent discrete features, so things like points, lines that may represent a stream, or polygons that might represent buildings or property boundaries or watersheds, things like that. We also use gridded or raster data that's really comprised of data values for individual pixels, which may be very small in the case of an aerial photograph, and you see an image, although this is really just a bunch of different colored squares. Raster information can represent things like land use, like rainfall, like the elevation. And there's many other data types that are used in GIS that we won't get into that much. Multi-patch data, triangulated regular networks, annotations. There's really three views of GIS that I'd like you to think about. The first is the geodatabase view, how we structure data sets to represent geographic information in terms of a generic data model. Then there's the visualization view, basically making very attractive looking maps that convey information in a concise and compelling way, that serve as a view or a window into the database to support queries and analysis. And then there's the geoprocessing view, which are information transformation tools that derive new geographic data sets from existing data sets. These are all the tools that we work with. And GIS comprises all of these three things, and how the data is organized in databases, the visualization and the tools are all integral parts. This is an example of some of the tools for automation of repetitive tasks. So here we might start with an elevation data set, convert it into a GIS format, then calculate things like the flow direction, the slope, and the aspect. And if this is something that's been done before, you may use it for automation. You may also use programming to implement functionality not available. For example, you come up with something creative. That's what got me into GIS to some degree. I was interested in calculating and looking at some of the properties of stream networks, and there wasn't functionality available to get that information out of GIS, so it had to be programmed. I've used the word data model. So what is a data model? You may have somebody who says, "Can I please use your data?" And perhaps they give you the data like this. Can you do anything with it? It's just a bunch of random numbers and nondescript columns. I would posit that you can't do very much with this. You really need the metadata, information that tells you about the data to be able to use this. And the data plus its metadata effectively comprises a data model. To bring that home, think about a watershed and a stream. So a watershed has an outlet and a boundary, and then there's a stream that follows down the valley. If we think of the data we may gather, we might measure observations of stream flow at the outlet. And this is ironic because this is actually dry canyon where there's never been any stream flow in all the years that I've looked at this. I live quite nearby to that. That's the water research lab in the bottom left corner. But you may measure stream flow at a gauge at the outlet, and you start trying to construct relationships between the various objects. There's a stream gauge at which you measure the flow values. That stream gauge is a sampling feature, and that information tells you something about the flow in that stream, the feature of interest, which may be a line, or the flow originating from that watershed, which may be a polygon. So once you start constructing these relationships, you're building effectively a data model. So ArcGIS uses a data model based on a collection of data themes. You'll see when you're working with it, streams, hydrographic points, drainage areas, sometimes they're referred to as layers that all sort of layer on top of each other, and you get an integrated perspective on that particular specific place that you're studying. And it's that integration of information at the place you're interested in that is what makes the system so powerful. So this is getting us into the concept of information frameworks. We might think of a conceptual model as a set of concepts that describe a subject and allow reasoning about it. A mathematical model as a conceptual model expressed in symbols and equations. Then a data model is a conceptual model expressed in a data structure, for example, ASCII files, Excel tables, or a database. And then you have a geographic data model that's a conceptual model for describing and reasoning about the world expressed in a GIS database. So it all starts from conceptualizing what it is we're working with. So in this idea, we conceptualize to be working with a stream gauge, with streams, and a watershed. Those are concepts that exist before you go to the computer encoding of them. And a data model is important because the way that the information is organized can enhance or inhibit what you can do with it. This has been really fundamental in the construction of ArcGIS and other geographic information systems. And this is a picture of Scott Morehouse, who was the original information architect of that. And he has a quote that he wrote at the preface of one of David Maidman's books about geographic information systems being built on formal models as an abstract, well-defined set of concepts. And it really defines the vocabulary for describing and reasoning about the things that are located on the Earth. So here are some of the models underlying geographic data. Vector format data, maybe a point with X and Y pairs, a line as a sequence of points, a polygon, a closed set of lines. Contrast, here are some examples of that. So we might have flow stations along canals, polygons that represent the areas drained to them in a particular watershed in Florida, where it may be getting very wet from the hurricane that's about lurking offshore in that area. You might be interested in the attributes of a specific feature. So you might click on a specific polygon, and then it'll tell you which watershed that's part of, and various other things like its area, its length, and other encoding that I don't know what S65A stands for. There's also raster data, and raster data is represented in terms of typically grid cells that may be square, sometimes rectangular, and polygon can be represented as a zone of grid cells. A line can be represented as a sequence of grid cells, and a point as a single grid cell. So there's a sort of comparison or sort of opposite representations of discrete data that's often represented with vectors, such as a lake and a river and a road and a building, or continuous data such as topography that's often represented with raster information. So there's two fundamental ways of representing geography as discrete objects and fields, spatial fields. So here we have the discrete object view represents the real world as objects with well-defined boundaries, whereas the field view represents the real world as a finite number of variables that are defined at any location. So we can think of the real world out there, and what we're doing is we're abstracting it and approximating it to encode it in a computer. And these are two different ways of doing that. When you're using raster data sets, you have to encode the value at each grid cell, as well as the number of columns, the number of rows, and the cell size, and then you have all the information needed about that particular data set. Here's an example of a raster data set from the Shuttle Radar Topography mission that in about 9 days mapped the topography of the Earth. Or in 9 days of the shuttle flying, collected all the data, and it was many years of processing before the data was released and made available. I've worked a lot with digital elevation model data, and that's a special type of raster data. And over the years, it's been interesting to see the growth in resolution, starting in the 1980s, where Defense Mapping Agency had a spatial resolution of 90 meters, 100 cells per square kilometer, and a 50,000 square kilometer watershed would be 27 megabytes. That's pretty small. Although in those days, 27 megabytes wasn't actually that small. Then we got the 30-meter digital elevation models come out from the USGS in the 90s. 2000, we got 10-meter data. And now we're working with 1-meter LiDAR data, and you're getting a lot more detailed resolution. But the same watershed would now occupy 200 gigabytes. That does actually challenge your computer and being able to work with it. There's been a factor of 10,000 increase in 30 years. So we're still pushing the limits of computation and trying to be efficient in the tools that we work with this data to be able to get information out of the sort of rich detail that we see in this data. So this is a screenshot from the help page of Spatial Analyst, which is one of the tools that's part of ArcGIS that lets you work with elevation data. And from an elevation raster data set, you can calculate things like the slope, the aspect, the hillshade, which was depicted on the previous slide. And that's part of the geoprocessing approach, where you are creating new information based on raw data. And it's often been wonderful to me how you can start with what I think of as fairly dumb elevation data, height values on a square grid, and then you can calculate where the water would move. You can calculate things like the slope and the flow directions, and you can delineate watersheds. You end up with quite a rich data structure that allows you to analyze hydrologic properties of the area that you're interested in. So Spatial Analyst enables analysis of the land surface terrain as a grid, and it's useful for defining drainage areas, connectivity to the stream network, and many other things. So we've talked about points, lines, and polygons. Here are some lines, and here are some polygons representing water bodies and watersheds. We've also talked about digital elevation models. How do we combine them? Maybe you want an integrated raster vector database. And this is where the concept of a geodatabase has been introduced. And it's really part of organizing our information in a coherent way. So a geodatabase lives within a workspace that's typically a folder or directory on your computer. A geodatabase can be in any one of a number of file formats. This MDB is a Microsoft Access database, more commonly as a file geodatabase that goes with the acronym GDB. Then within it you have feature data sets that are effectively collections of feature classes. A feature class is a single layer of similar objects, such as a set of points that maybe represent points of interest, stream junctions, for example, or something like that. They may represent a network that has flow direction associated with it. There may be relationships There may also be tables referred to as object classes that don't have any spatial information associated with them unless you make that link in the database. So an object class has a collection of objects in tabular format. So with databases, it's all tables and values and then key values that allow this parameter to be associated with another table. A feature class is the name we give to a collection of geographic objects. And in addition to the tabular information about the thing that you're interested in, there's also shape information. It says it's a point or a line or a polygon. So feature class is an object class plus spatial coordinates. So how is this evolution in the thinking of geographic information systems sort of evolved at ESRI? In the early days, long before I actually even started working with ArcGIS, there was ArcInfo that was the basis of the founding of the company, and there were versions 1 to 7 from 1980 to 1999, and there was an Arc macro language. Then to help make it more user-friendly and work on PCs, ArcView was developed and went through versions 1 to 3 from 94 to 99, and it had a scripting language called Avenue, and that's where the shapefile came from. The shapefile has been one of the real popular file formats because it was made open and anybody could construct a shapefile and work with it. Then came the ArcGIS, which tried to combine those concepts and become a bit more user-friendly, and there were versions from 8 to 10, and that's manifested by the sort of ArcMap software that's really introduced geovisualization, the geodatabase, and geoprocessing as separate components. Then when computers started switching from 32 bits to 64 bits, ArcGIS Pro came out, so that's the first 64-bit software, and it's really rebuilt from the ground up to take advantage of 64 bits. And that's been around for about 4 years now. It came out in 2016. So we're using this one because it represents the sort of the end of the evolution and where all the new capability is being built. So this shows the ArcMap, ArcCatalog, and ArcToolbox separate components of the ArcMap system. And then ArcGIS Pro is a single integrated project environment where you have a folder for your project with everything in it. So also with ArcGIS, there's ready-to-use tools for anywhere in the world. So there's a lot of data available as well as web-based services. And I was just trying some of that out before the class to sort of see what that is. And I'm going to sort of break out of that into a quick demo at the risk of going over time here. What time do we finish? I'm all confused because of I finish at 6:30. Okay. I'm all confused because my computer clock is different from my watch because I'm not actually sitting at home. So what I've got here is this is actually the map that's part of the Learn to Use ArcGIS exercise that I have guided you to do. And this is the Amazon basin. And down in the bottom right corner, you can switch between the sort of catalog that shows you the various data sets that you have. And in geoprocessing, you can find a portal which has ready-to-use tools. And this will do watershed delineation based on data in the ESRI cloud. So this is running in some cloud service somewhere. I think it's probably hosted as part of Amazon Cloud Service. Ironic that we looked at the Amazon basin, but we don't actually know where it's located. So I'm going to zoom close in, and I did this trace downstream earlier so that I could have a point to click on the Amazon River, and I'm going to try and delineate a watershed, and I'm going to specify an input point by clicking on the map somewhere near the outlet of the Amazon River, and then I'm just going to say run. So this is now running this tool on data that's hosted in ESRI's web services, but it's running the ArcGIS Pro desktop client, so it's interacting over the network. If I was not connected to the network, this wouldn't work. This is also taking advantage of the fact that I'm logged into my ESRI account, and I have a small number of computation units assigned to me to be able to do this. So one of the things that we'll have to work out with all of you is whether your accounts let you do this or not. And if they don't, we might have to see if we can see what needs to be done to get you a few of the units. I don't think it uses very many units. So we see what happened with this particular tool completed, and it's added to my map an outlet snap point and an output watershed, which I can zoom to the layer of. And there I have delineated the Amazon River Basin to this point that I was interested in. And then I could do various interesting things with it. So ESRI has built a web service for effectively pretty quickly. It only took 10 or 15 seconds or so, maybe a minute, I don't know, to delineate a huge watershed. That is actually pretty remarkable. Wasn't possible 5 years ago, and certainly not 20 years ago when we started working with digital elevation models and thinking about watershed delineation. So these are some of the ready-to-use tools that ArcGIS provides. Effectively mapping on the web. So there's a lot that can be done without even having software on your computer, just with effectively web-based, browser-based work. And that may be the way of the future. If we're collaborating on writing a scientific paper, we might work in a Google document where many people can work on it at once, and we don't actually know where it's stored, somewhere in Google's cloud services. Mapping may go the same direction. There's also a living atlas, which is where anybody can contribute data that they have assembled and make it available for other people to use. So you can get a lot of hydrology data from the living atlas, as well as lots of other information. So I'm going to take the remaining time in this to now jump into some of the details of geographic information systems, just by way of effectively recapping and covering some of the basics. And one of the topics we encounter a lot in geographic information systems is coordinate systems. How is information represented spatially? And that's also sometimes referred to as a spatial reference system. So we live on the Earth that's approximately a sphere. Later we'll talk about it being a spheroid. And through the accidents of history and geography, we use the prime meridian going through Greenwich, England, as the origin of longitude coordinates, and we use the equator as the origin of latitude coordinates. So there's this point out in the Atlantic Ocean that's 0, 0 in terms of latitude, and longitude. So we measure latitude in lines that are referred to as parallels. So you may be 30 degrees north of the equator, 60 degrees north of the equator, and so on. We measure longitude east or west from the prime meridian, also in degrees. So the range of longitude can be from 180 west to 180 east. The west longitudes are often given negative numbers, and then latitude is from 90 south to 90 north, the southern hemisphere, given negative numbers. So if somebody tells you they're at latitude 95 and longitude 45, you know that they are wrong, because you can't get a latitude bigger than 95, but you can get a longitude that way around. So Logan happens to be at latitude 41 degrees north, longitude 111 west. Austin is those numbers. We think of the Earth as a sphere. It's actually a spheroid, which means it's slightly larger in radius at the equator than the poles. It's sort of bulging out a little bit, and that's due to it rotating. The rotation of it causes the effectively centrifugal effect causes the effectively water and moving parts of the Earth, and we've got sort of magma and plate tectonics. The Earth is a malleable blob, and it expands out because of its rotation. So it's a spheroid or an ellipsoid, and that's defined by basically an ellipse that's being rotated. So an ellipse has a focal length, the distance from its center to one of its focal points, and it has two axes, a major axis, which is the sort of longer radius, and the minor axis, which is the shorter radius. And then there's a flattening ratio, which is effectively the difference between those two scaled by the major axis. For Earth, the flattening ratio is only about 1 in 300. So the minor axis is only 1/3% shorter than the major axis. So it's only slightly distorted from a sphere. Take that ellipse, rotate it around its minor axis, and you get what's referred to as an ellipsoid or spheroid. There's a number of standard ellipsoids that are used in working with geographic coordinate systems, and those came about historically as people were studying this. First, Clark in 1866 established the Clark ellipsoid, which has these parameters. Then in the 1980s, the Geographic Reference System established a different set of parameters that sort of better approximated the shape as people got to understand and survey the Earth better, and started putting up satellites that things could get measured a whole lot more precisely. So we talk about geographic coordinates as the latitude and longitude defined using an ellipsoid, which is an ellipse rotated about axis, and then the elevation is defined relative to a surface of constant gravitational potential close to the surface of that ellipsoid. Then we refer to Earth datums that define standard values for that. So when we talk about the Clark datum or the GRS 1980 datum, it's referring to those specific parameters. Latitude is defined, once you're talking about an ellipse, the angle that goes from, if you draw a line from the center of it, you won't intersect the surface at right angles. So latitude is actually defined by taking a line at right angles to the surface and seeing where it intersects with the the major axis and measuring that angle. So it's the angle that line makes with the equatorial plane. That's just a sort of subtle definition of latitude, and that comes about because the way we really measure latitude on the surface is by observing things like the stars and the sun, and looking at that relative to horizontal on the Earth, and it's the horizontal on the Earth that we're measuring. We can't really easily measure an angle to the center of the Earth. Longitude is measured around from the central meridian through Greenwich, England, and it's a sort of angle between a cutting plane of the prime meridian and a cutting plane on the meridian through the point you're interested in. So there's horizontal Earth datums. We talk about the North American datum of 1927, the North American datum of 1983, as we started getting a better understanding of the Earth, the World Geodetic System datum of 1984. It's almost the same, but differs in subtle ways. And we also, given that the flattening ratio is quite small, we often think of the Earth as a sphere with the parallels of latitude and longitude, and that lets us get sort of approximate distances based on spherical geometry. So if you're approximating the Earth as a sphere, you can calculate the length on a meridian, which is a north-south length from points A to B, as the radius of the Earth times the angle, and if you put that angle in radians, the change in longitude, you'll get the change in latitude, delta phi, you'll get the north-south length. For calculating lengths on a latitude parallel, you take the radius of the Earth at that latitude, which is the actual radius of the Earth times the cosine of the latitude, and then multiplied by the change in longitude. So the effect of that is that as you get further north, the same distance gets smaller. So here's an example that works out for a 1 degree increment at 30 degrees north, and you can go through the math and you find out that the longitude distance is about 111 kilometers and the latitude distance is about 96 kilometers. So parallels converge as the poles are approached. And you can think of 1 degree as approximately 100 kilometers depending on where you are on the Earth. This is, it's approximate because the Earth is not really a sphere. ArcGIS will actually do the calculations based on the ellipsoid for the specific projection being used. So that gets to the point of map projections. All of what I've spoken about so far has looked at latitude and longitude on a curved Earth. A lot of what's done with GIS is effectively flatten out the Earth onto a Cartesian plane and work with projected coordinates. So we have a planar coordinate system defined by a pair of orthogonal XY axes drawn through an arbitrary origin, often someplace close to the area that you're interested in. And we approximate the curved Earth on a sort of a two-dimensional surface. That introduces distortion, and that leads to difficulty in precisely defining things like length and area in geographic information systems, because it comes down to what projection you are using. But we have to pay attention to and know all of that. So there's a number of types of projections. Conic projections that effectively use a cone to flatten out the surface, cylindrical projections that use a cylinder, and then azimuthal projections that are good for sort of global global views. So the idea behind a conic projection is that you've got a sphere or spheroid that is the Earth, and you put a little cone on it, a top hat, an ice cream cone, if you will. And then you unroll that, or you perhaps shine a light from the center of the Earth to map each point on the Earth onto this cone, and then you unroll that, and that becomes a representation on a plane of the curved Earth surface. I'm not going to go into a whole lot of details of projections. There's a lot of interesting pictures one can look at, but it gets us into that when we're working with locating a point horizontally on the Earth, which is where we talk about horizontal coordinate systems. You've got geographic coordinates that you need a horizontal Earth datum, things like the ones I mentioned previously, as well as projected coordinates where you may have XY coordinates, or sometimes referred to as eastings and northings, east from the origin and north from the origin, and units of meters or feet. And they have names such as Albus Equalaria or transverse Mercator, depending on the specific technique used for representing the curved Earth as a flat surface. I don't want to get too bogged down in coordinate systems given the time available, and given that ArcGIS actually takes care of a lot of it for you. So what you really should know about coordinate systems is that there are many. Each is specified by distinct, pretty jargon-laden parameters. For the location of something to be fully specified on the surface of the Earth, you need to know what the coordinate system is and what the location is relative to that coordinate system. And GIS will take care of a lot of that for you. It can facilitate the coordinate system transformations. So what I think that we really need to know for sort of practical purposes as engineers and hydrologists is to recognize coordinate systems by their names and parameters and the associated numbers and values associated with the parameters. But for this class, do not worry about the details. You'll see with coordinate systems, there's a lot of numbers associated with it. And really the important point is, as long as those numbers are specified and the name is known, well-known coordinate system, for example, you shouldn't get bogged down in the details too much. But sometimes we'll have to pay attention to that, because you'll get data in one coordinate system and data in a different coordinate system, and without converting one to the other, the two will not work together in a smooth way. So actually paying attention to what the coordinate system is quite important, but knowing the specific details of the parameters is not. So now I'm going to use the last part of the lecture to talk about some of the data sources for hydrology and water resources. So when we're building up the base map in the class on Thursday, we'll go through some of these. So there's a hierarchical system of watersheds and basins used in the US, and I'll just touch on some of that. And I'll also talk about where to obtain some of the data and maps that we use nationally in hydrology for things like hydrography. Hydrography refers to the blue lines on maps, the streams, the lakes. Then there's the USGS National Water Information System, which is where you get stream gauge information, what's measured at a particular location. There's land cover data, there's elevation, and then there's many others that some of which you can get into if you're interested, things like census information, road and traffic information, but we're keeping our focus here on hydrology and water resources, so we won't get into that. So the national map is this website that's effectively a central source for much US government data. And it integrates together things like the National Hydrography Dataset, all of the information that's known about the rivers and streams in the country, the three-dimensional elevation program that gives you the surface, the topo maps. It also has some historic information, and it allows you to find, view, and download data. So I could click on that link, and here we can get into the national map. You can find the national map viewer, and perhaps you can decide that you want to download data. So it switches to a different viewer, and I don't know, I've still got a spinning wheel here. Maybe I shouldn't go into this for too long, because it's going to eat up my bandwidth when I'm trying to record video and webcast this. When this eventually gets its data downloaded, I was going to zoom in on an area and show you how to download information of interest. Maybe I'll leave that chugging away for a while and keep going with the slides. There is the Watershed boundary data set. So the agencies dealing with water in the US, which is largely the US Geological Survey, the Environmental Protection Agency, the Natural Resources Conservation Service, FEMA, Army Corps of Engineers, have all effectively worked together to delineate the country into river basins. So, for example, there's the Upper Colorado, the Great Basin, the Texas Gulf region, Missouri, Upper Mississippi. Each of those is encoded with a number ranging from 1 up till about 22 that's referred to as a two-digit HUC, or two-digit hydrologic unit code. So I happen to know that the Great Basin, Logan, Utah, is just north of Salt Lake City and north of the Great Salt Lake, is number 16. Upper Colorado is number 14. The Texas Gulf is number 12. And if you look at the national map, you can see those numbers. So the watershed boundary data set starts from those, but then based on the watersheds, delineates into very many smaller units that are then also numbered, and you end up with 4 digits. Let me go to the next slide, probably. So you start up with the 2-digit regions. Those are divided into things that require 4 digits to specify them, then 6, then 8, 10, 12, and so on. So we refer to an 8-digit HUC, or hydrologic unit code area, as something that's about the size of a county. This particular one happens to be in North Carolina, and it spans from just west of Raleigh, Scott Durham, Chapel Hill, all the way to Greensboro, a distance of about 50 miles or so. Then you can look at a Little Creek NHG plus catchment that's a whole lot smaller than that. So you get 8-digit watersheds, 10-digit watersheds, 12-digit watersheds, and so on. They've been delineated from the National Elevation Data Set, and often hand-checked and edited to make sure that they're consistent. So these are the encodings of the high-level watersheds, and this is talking about the National Hydrography Data Set, which is the streams for the nation. And we're in a process where the agencies involved are rolling out high-resolution national hydrography data sets. And wherever it's blue, it's available in beta format. Where it's this yellow, it's in production, and there are a few places where it hasn't been started yet. And that was as of a year ago. So there's probably been considerable progress since then. And we'll work with some of this data that you can actually download from the national map, so you get familiarity with that. So here you can see with quite incredible detail how some of the streams are represented within 8-digit HUC watersheds. So within the National Hydrography Dataset, one of the interesting things about it is everything is given a sort of a double-barreled name. Rather than just calling something a river, it's a stream river represented as a line, or a spring seep represented as a point. Sometimes they create artificial lines going through reservoirs. You might have a submerged stream. So there's they've got encodings for all of these, and these are what the attributes are that are associated with the data set. Let me go and see if anything's happening with that download. No, it's still just chugging away, so we'll not worry about that national map. Or maybe I should zoom in on a slightly smaller area and see if I can get any luck there. So if I zoom in around about Logan, and then I switch to the data download mode. Okay, there we go. Now suddenly it came back with zoomed back out again, but I can zoom in, and these are the sort of this is the sort of information that's available. So you can get hydrography, the NHD plus high resolution data. You can get elevation data. So maybe I'm interested in the high resolution or the hydrography information, and maybe I want to find the products that are available. It says I have to select at least one category. So maybe I'm interested in the HUC 4 subregion, and maybe I'm interested in NHD plus, and let's see if I try to find products on that. It'll go through a search and list for me the various products. So this is a bundle of data, and it tells you what size it is, it gives you a link to download it, and it gives you a bit of a thumbnail for the region. So we will use that to access hydrography data set in the exercise on Thursday. Okay, so where was I in the lecture? About there. So we spoke about. So this is just illustrates some of the things that the hydrography data set keeps track of. They use river reach codes. So just as you might say that you live at a certain address, 268 North, 1570 East, Logan, Utah. The addresses in Logan are actually north and east addresses, which is a little bit like latitude and longitude. If you want to specify a point on a river, you need to identify the reach of the river, and there's a unique reach code associated with it that's based on the hydrologic unit codes, as well as segments within it. And the location on the reach, the 0.392 means it's that fraction of the distance from the downstream end up to the upstream end. So it's a relative addressing, and to to precisely indicate a location on the river, you use that sort of information. Now, depending on how well that river is mapped, or if it meanders, or the meandering changes, that may not be that precise. But just as your house's address may also change as you get more information. So this is the national elevation data set. So the National Hydrography data set was vector data, meaning it's represented in terms of points, lines, and polygons. The National Elevation data set is raster or gridded data, and this gives you the elevation of the surface of the Earth over the area that you're studying. This happens to be part of the river that I'm not going to try and pronounce in Louisiana. This is part of a national elevation data set, 30-meter digital elevation model. And when we say it's a 30-meter resolution, it's often specified in terms of arc seconds. So an arc second is 1/60th of a minute, and a minute is 1/60th of a degree. So it's 1/3600 of a degree of latitude or longitude. And if you work that out, you'll work it out. It's roughly 30 meters. And we can use those formulas that I showed when I was calculating distances for latitude and longitude to work that out. Then there's some high resolution. 1/3 arc second is about 10 meters, and 1/9 arc second is 3 meters. And those are distributed as part of the national map, and there's billions of data points derived from 1 in 24,000 quadrangle sheets, or at high resolution from LiDAR. So you can actually look at the national elevation data set availability on the national map viewer. There's also a distribution of the national hydrography data sets made available from Horizon Systems, which is the company that's been the contractor to the US, to the government agencies, the USGS and EPA, in terms of providing this data. So that's also sometimes a source for the data. That's if you want to get large chunks of data, it might be better to get it from this source than sometimes the national map. So the National Hydrography Dataset Plus is actually becoming a foundation for what's referred to as the geospatial hydrologic framework for the United States. If we think of the watershed boundaries, the elevation data sets, the land cover, and the hydrography, you can put them all together and you know almost everything you need to know hydrologically about a watershed. And that's incredibly useful for things like hydrologic modeling, water quality modeling, and also tracking changes over time as we see perhaps the watershed changes due to land cover, land use change. And there's a roughly 2.7 million reach catchments, average area of 3 square kilometers, and the national hydrology, or the national water model that's being constructed and run at the National Water Center in Tuscaloosa, Alabama, models each of those. So the basic model element is this NHG plus catchment, and there's 2.7 millions of them, and running on a supercomputer to effectively tell the state of the country's water and provide forecasts in real time across the country. So this is how you can download data from Horizon Systems. You click on the region that you're interested in, and it'll take you into the downloading of it. So I'm going to sort of end off with a bit of discussion of digital elevation models. So a digital elevation model is a representation of the surface of the topography on a grid, typically a square grid, where you have postings of elevation, numbers 711, 708, 705, and so on, that represent the land surface. You might have contours that go through them, and it may be that these elevation values were derived from the contours or vice versa, depending on how the data was produced. So this is a gridded or a raster data structure. This shows a digital elevation model for Nebraska, and you can see just from the color scheme used, you can start learning a little bit about the geomorphology. You can see sort of wide river floodplains, and then there's a sort of steepish area, and you can see how the drainage is all from west to east in a fairly sort of uniform type of surface with rivers etched into it. In hydrology, we like to go to a single grid cell and then examine where water might flow if you're taking the model that it flows to one of its downslope neighbors following the steepest direction. So you calculate the slope from the center grid cell to each of the neighbors, and then you pick the steepest one. And then you encode that with a number. The 1, 2, 4, 8, 16 encoding is what ArcGIS uses for that. So that's referred to as the 8-direction 4-point model, or D8, or single flow direction model. And if you color encode that, you get something that's starting to tell you a little bit about the topography. You can see here the red shades are the sort of north facing, and the gray shades are south facing based on that encoding. With those flow directions defined, you can do things like calculate how many grid cells drain through each grid cell, and perhaps pick a threshold and map streams and identify the watershed. And that's what we did running the software for the Amazon. So delineation of streams and watersheds on a digital elevation model. We'll get into this a whole lot more later on in the course. Land cover. So the USGS Land Cover Institute, which is part of the USGS, has been effectively organizing and managing land cover data, and a lot of this is derived from Landsat, a satellite program that's been going since the 1970s. I think we're at about Landsat 8 or 9 these days. I'm not exactly sure. And that's at a 30-meter resolution and effectively tracking land cover changes over time. So you can see the land cover from 1992, 2001, 2006, and 2011, and look at land cover changes, and look at things like percent developed, percent impervious. That tells you something about the hydrology and how the hydrology may be changing. So land cover is classified using an encoding where these numbers are commonly used: 11 open water, 12 perennial snow ice. Then there's developed land cover, forested land cover, natural woody land cover, and so on. So we might get some of these numbers, and we might have to interpret these in terms of hydrologic parameters, for example, in our watershed, and we might be calculating what fraction of our watershed is say forested, because that tells you something about its hydrology. So then there is the National Water Information System. So this is now getting data that's not only geospatially located, but it's also time series. So this little map here, which if I expanded this with trepidation, since last time I followed a link, it's bogged down. But you can get into the map of all of the stream gauges of the US represented as each dot, and if we zoom in here somewhere around the Washington DC area, perhaps maybe we can find a stream gauge on the Potomac River. Well, let's pick a. So I don't know where this river is. SF Quantico Creek near Independence Hill, and you can go and access the data. So there was a map, and here you can get to the website that downloads the data. So there's a pretty impressive integration of information that you can obtain about the hydrology. And in the first exercise, we'll be looking at some of the streamflow data from the gauges in the Little Bear Logan watershed. So where was I? Back here. There's this USGS Water Watch website, which actually does a lot of that integration for you. That takes the daily data here for September 11th, about 2 years ago, and color codes it as to whether it's high above the 90th percentile or not. So you can get a sense of the spatial pattern. So this must have been after, I think this must have been shortly after Hurricane Florence. It's interesting that just 2 years later we're getting another hurricane on the East Coast. But you can see there was really high flows there. I'm not 100% sure of those dates, but that could be checked. So there you can see that there's high flows there, but other parts of the country are below average flows. And you can actually on this website go in and click on each individual dot and look at what the stream flow is. So here's what you can get. You can download the data in tabular format or graphical format. Then there's also the ArcGIS Living Atlas, which is where people can contribute data. The US agencies have also contributed a lot there. So the National Weather Service has a service for precipitation, NASA's Global Land Data Simulation System, 72-hour precipitation calculations, something else from NOAA. There's the ready-to-use watershed delineation service. This is the delineation of the Logan River. I showed you earlier the Amazon River. And there's the national water model from this website that's producing forecasts every 3 hours, I believe, running out several days. There's short-term forecasts that go out sort of just a few days at high resolution, then the longer forecasts are sort of coarser resolution for what the flow is going to be through running hydrologic models driven by the weather forecasts. Then also in terms of data, coming back to CUAHSI, the sponsors of this class, the hydro client is streamflow data in the Houston area here. And data.cuahsi.org allows you to access that data. And but the data and models used by hydrologists are quite diverse. Time series, geographic rasters, geographic features, multidimensional. So I've been working on developing the system called HydroShare, which is a general web-based hydrologic information system to allow anybody to effectively publish and share hydrologic data. It's at that website. It's a domain-specific data and model repository operated by CUAHSI. It lets you share data sets and other research products. It supports collaboration, has links to computational resources, provides permanent publication of data and models in support of your papers, which is what's being required nowadays by many journals, and links to computational analysis and reproducing the workflows in a Jupyter Hub platform. So these are some of the interesting things about HydroShare that we've been working really hard on, and it's a system to advance hydrologic science by enabling the community to more easily and freely share data products. So the age used findable, accessible, interoperable, reusable mantra. There's data from the US hurricanes that have been collected in HydroShare. So here's some CUAHSI websites to talk about that, and I'm going to flip through these quite quickly because I've probably gone on too long, but you can use story maps to talk about that. So what I've tried to convey to you today is that geographic information systems organize geospatial data in a way that enhances its analysis for many fields, including hydrology and water resources. As you work with GIS, keep in mind how the data is structured, what's under the hood. There's a plethora of data sources available, and GIS is about creating knowledge, telling stories, making decisions, all which involve integrating information from multiple sources. And in this module, I'm going to try and help you learn some of the GIS concepts and tools used in hydrology and water resources. So thank you. That was all I had in terms of slides. I'll exit from the slides and pause to see if there's any questions. Everybody's been really quiet.
I have a question.
Go ahead.
Okay. On slide, I think it's like 79. It's the map that shows the availability of the NHD. Yep. Okay. It says that some of it is close to statewide editing. Do you know what that means?
I could probably just get at interpreting those words. I think that that it probably means the agencies in the state are working on the data.
Okay. Closed. Okay. Yeah, it seems very specific to the lower Mississippi and California
And the Great Lakes region. Yeah.
Yeah.
So, or maybe it means that I don't know. It could mean that they have they are not letting those people edit it because they're in the process of trying to assemble it or something like that.
Yeah.
It could go either way. You might have to go and dig into that website a little bit more, see if they give a definition.
Okay.
Okay, I have a question.
Yeah, I have a question. I'm wondering if GIS has included other outside the US data available.
Yes. So the Living Atlas has lots of data from around the world, and we saw that here I did an analysis over the Amazon, which is outside the US, and this was using the analysis basically used the shuttle radar topography mission elevation data set underpinned that analysis, and that's available mostly worldwide. There's a little bit of near the North Pole and South Pole that's not covered. But yeah, there's a lot of data available worldwide.
Yeah, thank you.
Hey, David, I have a question about ArcGIS Pro. Do you know if it's backwards compatible with older ESRI software, ArcMap 10.6 or things like that?
Well, yes. I mean, I think depends what you mean by. So you can import an ArcMap document into ArcGIS Pro. So, and you can also import, the data sets are actually compatible both ways. So the geodatabases and the shapefiles and rasters are compatible both ways between one and the other. Thankfully, they're keeping the data sets. But one of the first things that's actually done in the in this where did I have it? in the Getting Started with ArcGIS Pro website is download this ArcGIS map document and import it into ArcGIS Pro.
Great, thanks.
I have a question.
Go
Quick
ahead.
question. Is the Living Atlas the newer version of what was the online geodatabase from the old ArcMap?
I
Like
think
the one that was accessible through the application?
I think so. Well, I think the Living Atlas is effectively a catalog for a lot of those online services. So when data goes into the Living Atlas, it actually ends up with a web service that is publishing it, and the Living Atlas effectively provides the metadata and description about it.
Okay, thank you.
Any other questions?
Could I ask one more question?
Go ahead.
While delineating the watershed, we are using DM and pouring point and something like that, but in the real life, we don't know how much water is available in the area. There might be less water than what we delineated with the help of GIS. How we can deal with that?
Well, so I'm not sure whether I'm fully understanding that. A watershed is a geographic object that's based on the topography, so it doesn't really depend on how much water there is. It's a delineation of the area that if you move down topography, you would get to that outlet. So now the calculation for how much water there is a whole nother story. It depends on the rainfall, evapotranspiration, infiltration losses, other sorts of things that go on in that watershed.
Actually, I meant while delineating, we have a bigger river basin, right, based on the and the potential streams that flows toward the outlet. But now with the effects of climate change or something like that, or human interventions, we might have a smaller area and which is not covered anymore by the real watershed delineated using DM. And can we just address in our modeling the boundary delineated from the GIS?
Well, so I guess there may be, for example, diversions or things like that. There are often interbasin transfers. And I don't know what's happened in the Amazon, but I know in the Colorado basin there are water transfers where water is diverted out of the Colorado River basin, and you may think of the water that drains to that diversion point as not being part of the watershed, but that would be a sort of a special case of some sort of a management or hydrologic infrastructure that's been built. Any modeling or calculation of the watershed would have to be sort of known and modeled explicitly. Are there any other questions? Is that big? I'm just seeing if I can open the chat and get a sense of how many chat messages there are. I've been seeing a few pop up. Okay. But there's a few about licensing, so I guess get in touch with your instructor, University of Washington. So I'll have to get in touch with Jessica Lundquist for that one. And then somebody has an older map document ran into an error, but there's a doctor to fix it. Well, that's good. Making software compatible is hard. Okay, well, I'm going to, there's not any more questions, sign off then. Sorry that I went a little bit over, but thank you for your participation, and I will speak to you all on Thursday. Last chance before I quit. Okay, thanks. Bye.
That's great. Thank you.